Hello, this is the Bioreactor. I'm Alex Cantor. I'm a biosystems engineering major.
Hi, I'm Greg Burke, and I'm a biosystems engineering major.
I'm Angelo Morrow. I'm a mechanical engineering major.
I'm Gia Penn, I'm an electrical engineering major.
I'm Yoni Wolf, and I'm an electrical engineer.
The goal of a stirred tank bioreactor is to provide a uniform mixture of nutrients and gases required to sustain a variety of cell cultures. This can include the growth of algae, mammalian cells, and fungi, which leads to the production of biofuels to create alternative energy sources, as well as alternative protein sources, and finally, pharmaceutical products. Now, the project goal is to advance the current bioreactor designs that are currently being utilized in research and in the market by developing a transforming impeller blade that is capable of producing a range of hydrodynamic mixing patterns to eliminate the disuniformity that is caused by the current fixed impeller blade bioreactors. Now to get into the scope of our project, we are developing a prototype bioreactor that has the ability to transform its impeller blades. We wanted to be able to demonstrate the variable mixing patterns that are generated, and we also wanted to create an easy-to-use interface to control the RPM that the impeller mixes at, as well as the angle change. We are also developing this in a water solution, and there will be no nutrient dosing and no sparger to create gas exchange. Shown here is our system requirements verification matrix. These requirements are split up into our parts, our performance requirements, as well as our electrical requirements. The main ones to take note of is the motor speed varying from 0 to 200 RPMs, our T-impeller being waterproof, the function of the T-impeller reaching from angles between 15 and 90 degrees, and the electrical requirements dealing with the LCD user interface, our GUI data display, and the automated feature within the system. We will touch on these further in the video.
We conducted a trade point design based on initial concepts provided by our sponsor, Dr. Quello. The first concept being the sliding card design, which utilizes T-cards which slide in and out of each blade to control the overall profile of the blades, which therefore controls the mixing within the tank. The second one being rotating propellers, which varies the pitch of the blades, similar to a helicopter propeller, which will therefore change the overall mixing in the tank as well. The third one is the expanding propellers, which utilizes a flexible membrane and mechanics for each blade to control the overall profile and width of the blades. We ended up choosing the rotating propeller design due to the unique hydrodynamic mixing capabilities of the design. By changing the pitch of the blades, we were able to adjust the amount of axial flow within the system, while the other two designs worked purely off of radial flow. The biggest difference between axial and radial flow, besides the direction of the flow as shown in the picture on the right, is actually the shear forces generated by each blade. Radial flow impellers generate more shear forces when compared to axial flow impellers. The amount of shear force a cell is able to withstand is actually different between cell types. For example, mammalian cells are shear sensitive, while bacterial cells are more suitable for a high shear environment. Therefore, by being able to adjust the pitch of the blades, we are able to provide an optimal growing environment for different types of cells as well as along their life cycle.
One of the major requirements from our sponsor for this project was to be able to visually show different mixing patterns at design day. We wanted to tackle this problem early, so we did an early prototype with a pickle jar, a bag of frozen peas, a Lego motor, and 3D printed blades to show that our design would provide visually unique mixing patterns at design day.
In order to properly scale our system, we conducted a dimensional analysis. This allowed us to identify the Reynolds number, which is the inertial to viscous forces within our system, and the power and torque requirements required of our motor based on the RPM in which the impeller spins at, as well as the diameter of the impeller. Based on our dimensional analysis, we are able to find that our optimal range of RPM would be between 0 and 200 RPM, and the impeller diameter would be 6 inches.
The system uses a V-belt driven pulley system with a motor and gearbox to power the rotation of the impeller. It then uses a linear actuator to control the angle of the blades. The linear actuator is connected to the inner shaft using thrust bearings to allow the inner shaft to continue to rotate while the linear actuator extends and contracts. The impeller itself changes the angle of the blades by connecting a 3D printed turnkey with a pressed-in pin to each blade shaft. These pins will be retained using 2 Delrin squares with cut channels to provide the actuation path between the fully vertical position and the flat position. These Delrin squares then just have to be aligned and then tightened with 4 screws to assemble the system, followed by putting on the bottom housing of the impeller.
Here we can see the electrical block diagram. We have our Arduino, our Raspberry Pi, and everything else is connected to those 2 items. We see the motor on the left with a power supply. We see below the breakout board and the touchscreen, and above we see the linear actuator. All of these are connected to a single power strip, which is connected to a 120 volt AC wall outlet. The Raspberry Pi also has a port on it for Ethernet connectivity. Here we can see our power analysis table. We use around an 80 to 90% efficiency for all of our calculations for power supply output and power supply usage. At the bottom you can see 500 watts total power used at around 115 volts, and that falls within our requirement for having everything powered off of 1 power strip connected to 1 socket. Here you can see our GUI. This is the manual control section where you can manually control the RPM and angle of the T-impeller. Using the tabs above, we can get to the automatic control section. This area contains a section for all profiles that are imported by the user, the current profile, and again, the start, stop, and e-stop buttons. Users can select the import button to import an Excel file containing RPM, angle, and time values. These can then be used to automatically run profiles with the specified RPM angle values for a specific time.
Our team custom made over 36 parts at the Biosystems fabrication shop this semester. We learned how to use the MIG welder in order to create the frame. We learned how to use the mill in order to create the blade extruders, as well as to create the slots in the frame, as well as to create the slots in the Delrin squares. Alex learned how to use the lathe in order to create the linear actuator adapter, as well as to size down the outer shaft to allow it to pass through the bearings and the shaft collar and pulley system. We also cut out the blades and baffles, as well as bending the baffles, and cut out and shaped the lid and lower baffle mounts. The outer housing for our T-impeller was professionally CNC'd by the AME fab shop. Lastly, we fully assembled and filled the system with water and used water beads in order to demonstrate the variable mixing patterns produced by our system. We'd like to thank our project sponsor, Dr. Quello, for providing us the opportunity to work on this project, our project mentor, Jeff Wolski, for guiding us along the way, and Mike Mason for providing his expertise in fabrication.